In model 21, we will continue with our study of RSM. We will go ahead and take up the concepts like first order design, then second order design, then first degree, second degree, and then the concepts of orthogonality will be a bit technical in our description of the model, and then slowly the terms and concepts will come up. So let's see what we have in this module. Again, it will be mostly in the form of MCQ. Okay, so let us start with understanding of the nature of response surface designs. The question number 1 reads like, in the context of RSM, first degree design means what? The presence of only one explanatory variable, the presence of only one response variable, approximating the response linearly in terms of explanatory variables, or none of the above. When you say first degree, so you are talking about linear involving many explanatory variables. Therefore, approximating the response linearly in terms of explanatory variables, that is the most plausible answer here, question 1C. In the context of RSM, first degree means response variable is binary. The presence of only one explanatory variable, which is again binary, modeling the response linearly in terms of explanatory variables, none of the above. In the beginning we said response surface study deals with response variable which is continuous, which is quantitative, as also all the explanatory variables are quantitative. Okay. There is no concept of binary response or binary explanatory variables. So A and B are ruled out. It is most plausible answer is C, which says that it deals with modeling the response linearly in terms of explanatory variables.
Okay. So in the context of RSM, second degree design means response variable is binary, or the presence of only two explanatory variables, or modeling the response as a second degree function in terms of explanatory variables, or none of the above.
So as you can see, second degree, the most plausible answer is item C, which says that you are trying to model the response as a second degree function in terms of all the explanatory variables. There is no question of the response variable being binary, nor the presence of only two explanatory variables. Okay, those are not tenable. Okay. The most plausible answer is item C.
Okay. In the context of RSM, second degree design means there are two response variables, the presence of only two explanatory variables, modeling the response as a second degree function in terms of explanatory variables, or none of the above.
So once more, the most plausible answer is item C.
So here is the fifth one. In the context of RSM, the concept of first degree orthogonal design, that is food, refers to a property of the response variable, a property of the explanatory variable, modeling the response as a first degree function in terms of explanatory variable, or none of the above.
So this word food, that should be read as first order orthogonal design. Okay. Therefore, over here the concept should be first order orthogonal design, which is abbreviated as food. Okay.
Yes.
So in the context of RSM, first order orthogonal design refers to a property of the response variable, a property of the explanatory variables, modeling the response as a first degree function in terms of explanatory variables, none of the above. Okay. So this first order orthogonal design that refers to a property of the explanatory variables, which are going to be mutually orthogonal to each other. They are allocations. Okay? Therefore, the closest answer is item B, which talks about a property of the explanatory variables.
So, in the context of RSM, again the first order orthogonal design food refers to a property of the response variable, a property of the explanatory variables in case they are qualitative in nature, again modeling the response as a first order, should it be first order function?
Yeah, first degree or first order
function in terms of explanatory variables, and none of the above.
So, here the closest answer is none of the above, because it does not refer to any property of the response variable. It is not talking about explanatory variables in case they are all qualitative, definitely not. They have to be all quantitative, that is the purpose of response surface. Modeling the response as a first degree function is not enough. Food means there is some extra property of the explanatory variable allocations. Regressor allocations, okay? So this property has to come. It is not yet manifested in any of the statements. It is none of the above.
Okay. So here for food,
Yeah.
Food refers to a property of the response variable, a property of the explanatory variables in case they are quantitative in nature, modeling the response as a first degree function in terms of explanatory variables, or none of the above.
So the closest answer is B, which says that a property of the explanatory variables in case they are quantitative in nature, because they have to have some kind of orthogonality property because of the nature of the design. Okay, it has yet to come, but the closest answer is B. Again the same question. What are the options?
The options are a property of the response variable, a property of the explanatory variables in terms of their independence, a property of the explanatory variables in terms of their combinations in design, and none of the above.
Yeah, the closest answer should be C, because it definitely it refers to a property of the regressors or the explanatory variables in terms of their combinations in the design, because that is how you will get orthogonality of the vectors. So if there are n data points, then each of these covariates will display n observations. That we will be getting column vectors referring to the first covariate x1, we have a column vector. For the second covariate, another column vector. All these column vectors are of dimension n by 1. N is the number of observations. And those vectors, they have to have some kind of orthogonality property. So it is a property in terms of the combinations of the explanatory variables in the design itself. Okay. The most plausible answer is C. We don't talk about independence because orthogonality makes sense, but independence is a strong word.
So here also for food, it refers to a property of the response variable, a property of the explanatory variables in terms of their zero pairwise correlation, a property of the explanatory variables in terms of their combinations in design, and none of the above.
Here the more plausible answer is property B, because it says that it has to do something to do with the pairwise correlation. Correlation 0 means covariance 0. It is talking about the zero covariance among the covariates. So it may be property B or property C. So one of these two options, B or C, is the more plausible answer here. You might think in terms of the option C because it refers to a property of these variables in terms of their combination. Or it could be in a way referring to the property B where you are talking about zero correlation means zero covariance, pairwise zero covariance. Some sense of orthogonality is coming through B.
Here again in the context of food ensures more accuracy in the study of RSM. It can handle linear regression efficiently, or it provides a powerful tool to examine the response surface, or none of the above.
Okay, let's see. If the response, the behavior of the response is truly linear in the explanatory variables, then if you think of y equal to alpha plus beta x, simplest case y equal to alpha plus beta x, and if x is assumed to is known to assume values in the closed interval -1 to 1, then it is not a difficult exercise to show that for a design which involves small n data points, then the most efficient choice of the values of x are in the two extremes -1 and 1. So 50% of the data points have to be generated by setting x at -1, and the 50% has to be generated by setting x at 1. That is the best possible allocation rule for most efficient estimation of the beta parameter in the linear regression model y equal to plus beta x. Extending that idea, if you are in the linear setup involving any number of covariates, for every covariate you need to have this kind of allocation rule, that 50% on one side that means at -1, and 50% at +1. Okay. That is the kind of rule. And then together with that, orthogonality would mean that they should be so blended that these vectors are mutually orthogonal in the sense of the inner product equal to 0. Okay. Therefore, it ensures more accuracy in the study of RSM. That is the most plausible answer here. Okay.
So the first one is
yeah.
And here is the next one. In the context of RSM, a second degree design involving two factors has 4 parameters, 6 parameters, 8 parameters, or none of the above.
So let's see what is a second degree design. So involving two parameters, two factors. Yes. The factors are x1 and x2. The model is y equal to alpha plus beta 1 x1 plus beta 2 x2. That takes care of the linear. Now we have to go beyond that to the second order. Okay, the second degree. So alpha plus beta 1 x1 plus beta 2 x2 plus beta 1 x1 square, beta 2 x2 square, beta 1 x1 x2. Yes. That is the end of it. Yes. So how many parameters do we have? Alpha, beta 1, beta 2, beta 1, beta 1, 2, beta 2, 2. That are altogether 6 parameters. That is how you have to count and you have to give the answer. Okay.
Here also we have a second degree design in context of RSM involving 3 factors. Okay. And we need to give the number of parameters. The options are 5, 6, 8, or none of them.
Okay. So there are 3 factors. We have alpha, and then we have all the singleton effects, beta 1, beta 2, beta 3. We have all the quadratic square term effects, beta 1, 1, beta 2, 2, beta 3, 3. Then we have the pairwise effects, beta 1, 2, beta 1, 3, beta 2, 3. Altogether 9 plus 1, 10. Altogether there are 10. It is none of them. Okay?
Yes. Here also in the context of RSM, a second degree design involving 2 factors will require for estimation purpose 6 distinct data points, 8 distinct data points, 10 distinct data points, or none of the above.
We have got 2 factors. This we resolved earlier. It is a second degree. So we are talking about beta 1, beta 2, beta 1, 1, beta 2, 2, beta 1, 2. 5 plus alpha 6. We need 6, at least 6 distinct data points. That is the whole idea.
So A is the correct answer. Yes.
So I will introduce one more related concept in the study of RSM. It's also called response surface design, but anyway, this is referred to as the property of rotatability of the response surface design. The idea is to assume a second degree model and then to assure that the fitted model enjoys what is called the property of equivariance at all points on the contour, that is the points equidistant from the origin, and for all such contours in the design region. Let me explain this concept first. Okay, imagine you are talking about the response y as a function of only 2 covariates or regressors x1 and x2. And suppose it is a quadratic regression. So you are writing y equal to alpha plus beta 1 x1 plus beta 2 x2 plus beta 1 1 x1 square plus beta 2 2 x2 square plus beta 1 2 x1 x2. This is your model. And x1 and x2, they both lie in the closed interval -1 to 1, both of them. So you start with small n data points. You write down x1 equal to etc., x2 equal to etc. So every pair generates an observation. x1 equal to this, x2 equal to this, generates an observation. Like that you have got n pairs. And you have generated the data. And you have fitted the, you have applied least squares principle and fitted the model, and you know estimates of all the model parameters. The moment you know the estimates, you can predict the value of the response at any point x by writing alpha hat plus beta 1 hat x1 plus etc. etc. And you can also work out the variance of the predicted response. Standard formula for, because you are in the framework of linear regression, linear model. So you can write down variance of y hat at a point x1, x2. This variance will depend on the designated point x1, x2, as well as it will depend on the variance covariance matrix of the estimates of the parameters in the model, and that will depend on the choice of your design. The endpoint design that you are starting with, the choice of the design will dictate the expression for the least squares estimates, and therefore their variance covariances, and that will enter into the expression for the variance of the estimated response at the point x1, x2. Rotatability means variance of the estimated response at a point x1, x2 will depend only on the distance of the point from the origin. That means it will depend only on x1 square plus x2 square. If it so happens that the variance of estimated response at any point x1, x2 is a function only of x1 square plus x2 square. In other words, it is a function of the square distance or the distance of the point from the origin, then this will be invariant at all points which are equidistant from the origin. Which depend, equidistant means x1 square plus x2 square equal to constant. Therefore, this is the property of what we call rotatability of the response surface design. So, a response surface design is rotatable provided the variance of estimated response is a function only of the distance of the point at any point is a function only of the distance of the point from the origin. It is a function of x1 square plus x2 square. For that to hold, we need a design of suitable type. Not any design will give a rotatable design. So, there is a huge theory underlying this thing. You can refer to the book by Das and Giri, also the book by Alok De talks about the rotatable designs. So, in model 21, in a sense, we have described different types of models, understanding the model which is described and then taking up an appropriate formula for the model expectation, counting out the nature of the parameters involved and the number of the parameters involved, and thereby looking into a framework for collection of data points and talking more about the number of distinct data points that have to be collected so that one is in a position to estimate all the model parameters unbiasedly. It is more or less an exercise in linear models subject to our understanding of the nature of the response surface. And we talked about the number of regressors starting from 2, 3, 4 onwards, etc. Depending on the number of regressors, the number of design points goes up, and then we have to suitably think about the choice of the design parameter, the choice of the points in the experimental setup, so that the response surface methodology can be suitably adopted and we can have an unbiased estimate of all the model parameters. That is mostly what we took up. So, in the next module, the last module, we will talk more about rotatability. We will come back to the rotatability concept and try to understand more of it. Yes, Sagarika, I believe most of these things will be made clear if we go through some questions. Let me read question number 1. In the context of RSM, write a short note on food, the first order orthogonal design, and illustrate the concept with 3 examples. Okay, to write a note, you have to understand what is first order orthogonal design. We are close to it through the MCQs in the broad framework. It says that, so let us start with 2 covariates, 2 explanatory variables, x1 and x2. And suppose we are talking about a set of 10 observations, for example. So y is a vector of 10 observations, and x1 has got 10 values in the range -1 to 1. X2 also has got 10 values in the range -1 to 1. So, for every combination of x1 x2, you have a value of y. That is the whole idea of understanding the regression. And in the model, we have alpha plus beta 1 x1 plus beta 2 x2. And we are supposed to have estimates of alpha, beta 1, beta 2. And mainly for beta 1, beta 2, the 2 estimates should be orthogonal in the sense that covariance of beta 1 hat, beta 2 hat should be equal to 0. That is the whole idea. So, you try to come up with examples where you can indeed show that yes, covariance of beta 1 hat, beta 2 hat equal to 0, because the moment you start with the values of x1 and x2, you are in the framework of a linear model, and you can find out the variance of beta 1 hat, variance of beta 2 hat, covariance beta 1 hat, beta 2 hat straight away, and then you can try to manipulate the levels of the 2 regressors in a way that this covariance becomes 0. So, you try out, for example, with 8 data points or 10 or 12 data points like that, and try to see what is coming up. Okay,
sir. So,
what is the next question?
So the next question reads, for a second order response surface design involving 2 factors, each with first order effects and 2 factors each with second order effects. Describe the model and count the number of model parameters.
So there are 4 factors, 2 with first order effect, 2 with second order effect. Very good. So I will have alpha plus beta 1 x1 plus beta 2 x2 plus beta 3 x3, beta 3 3 x3 square, beta 4 x4, beta 4 4 x4 square. That is what it says. So you know how many model parameters are coming up. Okay.
Yes, absolutely.
And then display.
So we need to display a design which provides unbiased estimation of all model parameters. Here we will assume that the factors are each lying in the closed interval -1 to 1.
Okay. So I know all the parameters, I know the model, I know the estimability condition, the rank of the matrix capital X should be full rank, full column rank depending on the number of parameters that are available. So you have to accordingly find out, we have to display the covariate the values of the regressors. We have to start with certain number of data points and come up with an example where we can get estimation of the model parameters. Okay, that's good exercise. And then what is problem number 3?
So here it reads, for a second order response surface design involving 3 factors each with first order effects and 2 factors each with second order effects, we need to describe the model and count the number of model parameters.
Very good.
Here also we need to display a design which provides again unbiased estimation of all model parameters. And here we will assume that the factors are each lying in the closed interval -1.
Yeah, I would say both the questions 2 and 3 are good exercises in the form of linear models.
Yes.
Estimability, basically estimability of the model parameters given a description of the model. Okay.
Absolutely.
What is question 4?
So here is question number 4. For a quadratic response surface design involving 3 factors, we need to describe the model and count the number of model parameters. Here we also we need to display a design which provides unbiased estimation of all these things.
Okay, let's see the difference between question number 2, question number 3 and question number 4.
Yes,
question number 2 says there are 2 factors with first order effect, 2 factors with second order effect. Question number 3 says there are 3 factors and then they have got first order effect and there are 2 factors they have got second order effect. Question number 4 says it is a quadratic response surface involving 3 factors.
Okay.
What does it mean? So apparently they all look similar, but there is a finer distinction. When you say quadratic response surface involving 3 factors, if the factors are x1, x2, x3, you have alpha plus beta 1 x1 plus beta 1 1 x1 square. Plus beta 2 x2 plus beta 2 2 x2 square plus beta 3 x3 plus beta 3 3 x3 square plus beta 1 2 x1 x2 plus beta 1 3 x1 x3 plus beta 2 3 x2 x3. That describes the quadratic response surface. It is different from whatever is said in the model description of question 2, for example. There are 2 factors with first order effects, so alpha plus beta 1 x1 plus beta 2 x2, that's it. And the 2 factors with second order effects, beta 3 x3, beta 3 3 x2 square, beta 4 x4, beta 4 4 x4 square. That was the description of the model. Okay, so you have to see the final distinction among the models as they are stated. Okay. And the rest of the thing is pretty obvious.
Yes, sir. So here are some multiple choice questions. Shall I read
Yeah, please read it.
Yes. So for a second order response surface design involving 2 factors each with first order effects and 2 factors each with second order effects.
Okay.
So the model parameters can be unbiasedly estimated assuming that the factors are each lying in the closed interval -1 to 1.
Okay.
The statement is valid provided the experimenter makes a selection of 12 distinct design points, or the experimenter makes a selection of 12 distinct design points including the central point 0 0 0 0, or the experimenter makes a selection of at least 15 distinct design points, or it might be the experimenter makes a selection of at least 13 distinct design points.
So let's see how many parameters are involved in the model. You have a second degree second order response surface design involving two factors, each with first order effects, alpha plus beta 1 x1 plus beta 2 x2, plus two factors each with second order effect. So beta 3 x3, beta 3 3 x3 square, beta 4 x4, beta 4 4 x4 square. That is the end of the model. So you know how many parameters are involved in the model. So in order to estimate those parameters from the model, etc., by applying the least cost principle, so the options are: the estimate, the experimenter makes a selection of 12 distinct design points. So all that we have to see, given the description of the model, we have to write out it in the form of a triplet, y x theta sigma square I, and we have to build on the matrix capital X, and we have to make sure that capital X has got it has got full column rank. Number of columns is the same as the rank of X. That's all we have to make sure. And the options are whether, if you give me the point 0 0 0 0, the central point, that takes care of alpha immediately. Because y at 0 0 0 0 is nothing but alpha plus error, so expectation is nothing but alpha. So at one stroke you know alpha. And hence from the model, wherever you have any other y, that y minus y at 0 0 0 0, that will take expectation, will get rid of alpha. So you don't have to worry about alpha anymore. Alpha is already taken care of from 0 0 0 0. That is the advantage of putting what is called the central point. Okay, it's a good tricky problem, but it's not difficult. Next one.
So the next problem says, for a second order response surface design involving three factors, each with first order effects, and two factors, each with second order effects, the model parameters can be unbiasedly estimated, assuming that the factors
almost
are
same
each
type of
line.
background, and they are giving options.
Yes. So shall I skip this? And
yeah, you can skip, because it's the same type of thing. And you understand the model, and then you have to make sure that you can estimate the model parameters unbiasedly, provided the kind of design points that you need and the nature of design points that you need.
The next one reads, for a second order response surface design involving four factors, each with first order effects, like similarly, and two factors each with second order effects.
So they are talking about 6 factors altogether.
Yes. And the model parameters can be unbiasedly estimated, here also assuming this thing. And we are given 4 options, like the experimenter makes a selection of 20 distinct design points, or it might be 24 distinct design points, including the central point 0 0 0 0. And the other one is he should take care of at least 23 distinct design points, and the fourth one is at least 24 distinct design
points. All that we have to know how many model parameters are involved over here in the model expectation of the response. And then depending on that, you need to figure out how many distinct design points you need. You need, the word distinct is very important. It's not enough to say I take 20 design points. I may be stupid to take one design point replicated 4 times. That gives no information on the model parameters. Of course, that gives information on the error, but that's a different issue. Okay, that's why the phrase distinct is very important.